3-1. Let's start there. Questions from 3-1? Anyone? 55? Sure. Okay, it says find the equations for both lines that are tangent to the curve y equals 1 plus x cubed and parallel to the line 12x minus y is equal to 1. So if I want equations for lines, I need a slope and a point, right? Well, the slope I'm going to get from my equation for a line that it has to be parallel to. Because what do we know about parallel lines? Equal slopes, yeah. So let's subtract 12x from both sides. And then divide by -1. So the slope I need is 12. Cool with that?
Yeah.
So the derivative is going to give me the slope at a given x, right? So the input is an x coordinate, and the output is the slope of the function y equals 1 plus x cubed at that value of x. So if I take the derivative of y, and then I plug 12 in and solve for x, that'll give me the location or the x's in y, where the slope of the tangent line there is 12, right? That's what I'm looking for. So I divide both sides by 3, and then we'll square root both sides. So those are my x's. Yes, Katie.
Wait, why do you plug in the
So what this is going to do, it'll tell me right? That's going to tell me the location, the x's in my function y equals, where the slope of the tangent line is 12. Excuse me. All right. So now that I have this, I have the slope, and I have the x coordinate. Last thing I need is the y coordinate, and then I can write the equation for my line, correct? How am I going to get the y coordinate for those x's? Plug them into the y equals equation, yes. So if I plug -2 in, I get -7. So there's my point, -2, -7. And when I plug 2 in, I get 9. So I have the point 2, 9. So now I just have to write the equation for my lines. So y minus y1 equals m times x minus x1. And then my second equation, y minus y1 equals m times x minus x1. And again, you could rearrange those so they're in slope-intercept or whatever, but you're done at that point. So if we think about what we have, we know these lines are going to be parallel to this line because they have the same slope, right? And they're going to be tangent to this one because the point that we found on y has the slope of 12. Is everybody okay with that? So again, here the calculus, very, very light, right? We just took like one little easy derivative. And the rest of this was like algebra skills. The hard part was keeping track of like, what information do I need? Where am I getting it from? What am I plugging stuff into? What does that tell me? That's the hard part, right? It's like processing, what information do I need? How do I get it? And where do I get it from, right? Does that feel better though, Casey?
Yeah, I think I just overthought it because I was just doing a bunch of stuff. I'm like, this is not right. Like, yeah.
These questions like this are often like, when you see it, it's like, oh, that was so simple.
Yeah.
To come up with it yourself,
Yeah.
you really have to kind of slow down and be like, okay, what do I really need to do this? And really kind of go like purposely through what you're doing. Oftentimes slowing down and thinking about like, what do I need to do to what do I need to have to answer this?
Yeah.
Is really helpful before just diving in and starting to do
Yeah.
stuff, right? Like, because there's like a lot of stuff you could do, but it's not helpful. Absolutely. Who's next? Audrey.
27.
27. Okay. All right, so here we have h of x equals x plus x to the negative 1, quantity cubed. So you should look at this and recognize that what you have here is not something that's in the form of a power rule. What you have is a composition of two power rules, right? Like I could take the derivative of x plus x to the negative 1, that's fine. And I could take the derivative of x to the third, but I can't, at least the way this is currently written, take the derivative of x plus x to the negative 1 quantity to the 1 over third. We will look at the derivative rule of how to do this, but that won't happen until, I think, section 3 or 4. 4. It doesn't happen to. But we can still do this problem. What we need to do is simplify this first. So I'm just going to FOIL this thing out. So what I'm going to use to do that is this multiplication prompt or pattern. So if I do that, h of x is going to be x cubed plus 3 times x squared times x to the negative 1 plus 3 times x times x to the negative 1 squared plus x to the negative 1 cubed. And I guess we'd probably simplify this down. To that. Now we're in a place where we can do the derivative. Since this is now just a sum of power rules, I can just do the derivative piecewise. So the derivative of x cubed is?
3x squared.
Good. And the derivative of 3x is? 3. And the derivative of 3x to the negative 1?
Negative 3 to the x to the negative 2.
Yep. And then the last one?
3x to the
Negative 4. Good. So that answer would be fine, but that's not the way that they would write this in like a multiple choice question. I would suspect this would be written with no negative exponents. Now, I wouldn't mark you down for leaving the negative exponents on it if it's a free response question. But if it's a multiple choice question, there's no way the negative exponent answer is going to be one of the choices. It'll be like what we've written there. And there's no way the answer in the back of the book had the negative exponents in it. I'm sure it looked like what I have written there. But I wouldn't mark you down in a free response section if you had the negative exponents. Once the calculus is done, you can be done. But if it's a multiple choice question, like, you know, you got to do enough to where you get, you know, which answer it is, kind of thing. You know what I mean? Does that feel okay, Audrey?
Yeah.
But just so you know, we are going to see how to do this problem directly without having to FOIL it out, because if that exponent was like a 7, ook is right. And we'll definitely have a method to do that problem without having to expand it out. So we can avoid having to do something that terrible, because nobody wants that, right? Nobody wants to know like the binomial theorem that well to where it's like, okay, I just do this in my head. Who's next? Katie. Yeah, I'm happy you guys are asking about all these ones that are later in the set. I think there are really some great problems in here. So here it says, show that the curve y equals yada 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 has no tangent line with slope 2. So, in other words, what this is asking is to show that y prime of 2 does not exist, right? If we say, show there's no place in the derivative that has a slope of 2, or I'm sorry, that's not what I want to say. Y prime of x equals 2 has no solution. That's what I want to say. Excuse me. Right? There's no value of x in the derivative where the slope is 2. Katie, does that feel okay? Okay. So let's find that y prime. So the derivative I can do piecewise. So the derivative of 2e to the x is 2e to the x. Very good. Derivative of 3x is 3. Derivative of 5x cubed is 15x squared. And you guys other than Chanel know these, right? When I'm asking? Yeah. Don't be afraid to shout it out. Like, it helps me to know. Okay. So what I'm going to do now is set that equal to 2 and try to solve for x. So how would I solve that equation for x? Sure, we could subtract the 3 over. What's going to happen after that?
No, that won't work.
Any ideas, anybody? No. No. It's already equal to -1.
Or like add 1 to each side and have that.
Yeah.
That's not helping.
So,
Nope.
What are you trying to do?
Solve that equation. 2e to the x. Yes! Let's graph this and just find an intersection, right? Or we could do this, right? Either one is fine. So if I try to graph this and look at this, and then we'll talk about how to do it without graphing it, but that's what would be my expectation from you guys. But we can do this without graphing also. So I'm going to graph this thing. I'm just going to do it on the standard window. Do you see it ever crossing the x-axis? No. Okay. That's the idea. Let's show you how to do this without graphing. Because assuming, again, always my assumption is this a problem that can be done with no calculator that could appear on a no calculator section? Absolutely it is. So I should be able to do this without graphing. Now, how would I graph this with no calculator? You wouldn't. What I would use is the intermediate value theorem to do this. So assume, for the sake of contradiction, that there is a point on y equals yada 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 where the tangent line, and let's just say y equals, or x equals a, where the tangent line at a, right, x equals a, has slope 2. Okay, I'm going to assume that it exists, right? That we have this. So, since y equals yada 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 is continuous, why can I say it's continuous? Continuous plus continuous plus continuous is continuous. So the first piece is continuous because it's exponential, and the second pieces are continuous because they're polynomial. Everybody's okay with that? The intermediate value theorem applies. So if I shouldn't say this yet. Okay, so I'm gonna do this, but I don't want to do it yet. So we have slope, someplace where there's slope 2. So we know that f prime of a also is equal to 2, right? So far, so good. So f prime of x was equal to 2x cubed plus 15x squared plus 3. And I set that equal to 2. And I have this. So far, so good. Just like we did. And now what we'll say is, okay, oops, except there should be an A here. I should say that's an A instead of an X. Okay, so that means then, because f prime is continuous, by the intermediate value theorem, there exists like a interval BC. Oh, come on, you stupid thing. I just want to erase this. Thank you. Where f of b is less than a less than, less than 0, less than f of c, and a is on BC. Did anybody see where the contradiction is going to come?
So,
It's going to be this piece right here. Notice that 12e to the x plus 15x squared plus 3. An exponential is always greater than 0, right? A quadratic, always greater than or equal to 0. 3, always greater than 0. If I add up 3 things that are all greater than or equal to 0, that must be greater than or equal to 0. That's my contradiction. There is no b in the real numbers where f prime of x is less than 0. Hence, there can't be any place where I have a slope of 2. And I lost everybody saying this, didn't I? Nolan.
For the greater than less than thing, would it be just f of b, or would it be f prime of b?
Oh, sorry, yes, f prime. Yes. Thank you.
So pretty much you took the intermediate value theorem and like why did you put b specifically there on the left and c on the right?
It didn't, it does, it's arbitrary.
Okay, so but if it's arbitrary though, like if you put like f excuse me, sorry, the derivative of b on the right side like greater than 0, then it would not be contradictive, but c would be contradictive.
Yes.
So, well, how would c be contradictive? Is it the same like idea?
Mhm.
Like okay.
Because there's no c that's going to make f negative, or f prime negative, right?
Okay.
Because f prime of x is always greater than or equal to 0.
Yeah, because this function will always be greater than 0.
Yeah, it will always be greater. In fact, yeah, that should be greater, strictly greater than. So I add greater than 0 and greater than or equal to 0. The result has to be greater, strictly greater than 0.
Okay. Thank you.
Because you can't add 2 zeros together. Yeah, but that's the idea. And how you would argue this without. It's just like, well, f prime of x, when I set it equal to 2, and I solve it equal to 0, I know it can't actually ever get to 0, because this piece is greater than 0, greater than or equal to 0, greater than 0, can't ever equal 0. And it's like an intermediate value theorem. I don't know that you'd actually have to quote it to get credit for it. Katie. If you had a calculator access, yes, that would be appropriate. Absolutely. Again, I'm always going to approach these problems like this. Like, what would you do if you had the calculator? What could you do without a calculator? And that argument of like showing something doesn't exist, like almost always is going to boil down to showing that like I can't solve this equation equal to 0. And the best way to do that is just look at each term and show that they all have to be, like at least one of them has, like they can't get a negative out of this or whatever. Like you can't get to 0 out of this because everything is positive. That's the idea. What else did you guys have? Well, I want to talk about 75 if nobody else is going to ask about it. This is the best question in the homework set. I wasn't so mean enough to put it on the homework quiz as making somebody responsible for doing this.
Is it hard?
I don't think it's that hard, but it is like, it's my favorite question in this homework set. And if you guys don't ask me about my favorite question, I'm going to definitely talk about it. So it says, let f of x equal the piecewise function x squared when x is less than or equal to 2, and mx plus b when x is greater than 2. Find the values of m and b that make f differentiable everywhere. What do I do with this?
It has to be continuously differential.
Okay, so the things we need for differentiability is f has to be continuous. What else do we have to have for f to be differentiable everywhere?
No vertical
No vertical tangent, excellent. And the last thing is jumps would be covered in the continuity. Can't have a jump, but we already got that when we said it has to be continuous. There's one other thing. What? Oh. No sharp corners. These three things you absolutely have to know. These are the three places where a derivative can fail to exist, or the three reasons a derivative can fail to exist, right? You have continuity, you have a corner, or you have a vertical tangent. Those are the three places where on a function where a derivative will fail to exist. That's something you absolutely have to know. That's a memorize. Okay. So if we look at this problem, only two of these three are really relevant for us in this problem. Which two of those three are going to be the ones that we need to worry about in this particular problem?
Continuous.
Continuous, absolutely. Corners, absolutely. Good. We can't have a vertical tangent just from having a piecewise function unless one of the pieces has a vertical tangent in it. You can't get a vertical tangent out of hooking two piecewise functions together, or two functions without vertical tangents in it together, right?
Like, what kind of functions would have vertical tangents?
For us, you should know the cube root, or really any odd root should have a vertical tangent in it. That's the only one I can think of off the top of my head. Maybe tan inverse. I'd have to think about it. It'd be something, though, that looks like this, you know, or I should say, I didn't draw it quite steep enough, like that. All right, so let's deal with these two pieces. If f is continuous, what property does it have to have? What's the definition of continuity? You have to know this. This is another one we have to have memorized.
There's no.
The limit as x approaches a of f of x equals f of a. Right?
Does that cover everything for it?
Mm-hmm. Or really, in this case, what do we know? What is the place where we have to? What is the a that we have to be concerned about in our function? 2. Why do I know I don't have to worry about anything else, Nolan?
Because anything below 2 is x squared, which is all continuous. Anything above 2 is x is just
Excellent. So x squared is continuous over its domain because it's polynomial. Mx plus b is continuous over its domain. It's polynomial. The only place we have to worry about is where those two meet and make sure they end at the start of one is the end of the other, right? So because this is a piecewise function, when we do our limit as x approaches a, what do I really have to do?
left and right.
Yeah, I have to do a left limit and a right limit because we are a piecewise function, and make sure that is true. Okay, so let's do this now. So the limit as x approaches 2 from the left of f of x is just going to be the limit as x approaches 2 of x squared, which is 2 squared, which is 4. The limit as x approaches 2 from the right of f of x is just the limit as x approaches 2 of mx plus b, which is just going to be 2m plus b. And then f of 2 is just going to be 2 squared, which is 4. So I know that 2m plus b has to equal 4. Well, because these three things have to be equal.
Yeah, but how do you?
Oh, I'm not done.
Oh,
Because we still have another piece that we still have to make sure happens, right?
yeah.
We need the no corners. Somehow that's going to have to give me one or the other so I can find either M or B using this equation.
Okay.
But I get another 2-variable equation that I'll solve a system with. But somehow I'm going to have to get the rest of this from the corners part. Everybody's okay so far? All right. No corners. How do I show that? Without graphing. Without graphing. Because I need to solve this algebraically for M and B, right? So graphing's not going to help me there.
Just find the equation of the tangent when x equals 2.
The left-hand limit of the derivative has to equal the right-hand limit of the derivative at all values A. So basically, we're continuous in the derivative, right? Okay. So, how do I do the derivative of f if it's a piecewise function like this? I just do the derivative of the first piece. What's the derivative of x squared? 2x. What's the derivative of mx plus b? M. So far, so good. So the limit as x approaches. Now, clearly, I should say, before I write this, well, first not writing. Clearly, when x is greater than 2, the limit is constant, right? Since it's just a constant. And when x is less than 2, I can just do direct substitution because I have a polynomial. So all I have to really worry about is at 2 is the only place where this might fail, right? Everybody's cool with that? Okay. So what can I say here? That m has to equal 4. If I take these together now, what can I say about b?
0.
Or negative 4?
What?
2 times 4 is 8. Right, when I plug 4 in for m?
Oh yeah. Oh, I'm so sorry.
That's okay. So there we go. There's my answer. There's my m and my b. This is a fantastic question because you have to use your definition of continuity inside of this. You have to use what you know about a derivative. You have to be able to evaluate limits inside, how to do a limit with a piecewise function. It's a beautiful, beautiful question. I love the heck out of this thing. Would I put something like this on your test? Absolutely. This is why I'm having us do it now together. It's not, and again, it's not even that many steps if you look at the work that I wrote down.
Yeah.
You just really have to understand what's going on to walk your way through it. But really it boils down to this. It's that I need to figure out the y or the m and the b that make f continuous before 2 and after 2, or make them equal before 2 and after 2. And then the same thing with the derivative, right? Again, when I take the derivative, I need the m and the b that make before 2 and after 2 equal. That's it. That's all I did. Right?
That's just, yeah.
And at the end of the day, all it really was me doing this.
How would you find the derivative of a piecewise function?
Take the derivative of the pieces.
Oh, so was the second part basically finding the derivative?
That's what we did right here when I wrote down the derivative, was I just took the derivative of each piece
So
separately
so m is the derivative.
of the second piece, because it was a linear function, right? Mx plus b. So the derivative of mx is just m times 1, and derivative of b is 0, because that's a constant.
Yeah.
So it's just m.
And since they have to agree that m equals 4, so derivative is 4.
They have to agree when at 2. Yeah. So I just plugged in 2 for the x and 2x, and that has to equal m.
Okay.
Would that be true for when you're checking any piecewise function for differentiability? That's what you really need to check, right? So you check for continuity with f. Just make sure that, that the start of one piece is the end of the next piece, or the end of the previous piece, I should say. And then you check the derivative and make sure that the limit of, the derivative at each piece matches the same way. And then again, you should give some thought to vertical tangent, but you're not going to get that from anything other than the piece itself. You can't get where the piece starts and ends, you can't make a vertical tangent unless there's already a vertical tangent. Like that you're splitting something with a vertical tangent half, and you have this half has it and this half doesn't, kind of, like.
And a vertical tangent is when the slope is vertical, right?
Yeah. So like the picture we drew.
Was that cube root of that?
Yeah. That kind of looks like that.
Yeah.
That has a vertical tangent, and that's the odd roots are the only. And maybe like one of the inverse trig functions or something. But it's pretty hard to draw, the question where you get a vertical tangent would more likely come with a picture that you just see it on there.
So if there is a vertical tangent, we just say we can't find a derivative.
The derivative there doesn't exist because there's a vertical tangent. And that's enough to just say that. What do you guys think? It's okay? All right, let's do 3-2. Yep. The next 3-2, 3-3, 3-4, I think are all just shortcut chapters. So the next shortcut we're going to look at is called the product rule. And it says that if f and g are both differentiable, then the derivative of the product of f and g is g times f prime plus f times g prime. Let's prove this. How do I prove one of these derivative rules? I start with the limit definition of the derivative. So if this is my function, everybody's okay there? What I'm going to do now is the tricky part. So here's the trick. is I'm going to subtract f of x plus h times g of x, and then add f of x plus h times g of x. Why is it okay to do that? So that's the part that's new. Why is it okay that I wrote that in there? Nothing to do with limit laws. It equals 0, right? Those two things combine to give you 0. So it's like doing nothing at all.
It's like multiplying with something.
It's like multiplying by 1, right? When we do make a common denominator, multiply by 2 over 2. It's okay to do that because you're just multiplying by 1. It doesn't change anything. I'm just adding by 0 here. I just wrote the 0 in a really funky way. All right, what I'm going to do next is I'm going to break that into 2 fractions. Oops. With a common denominator, as so. If I look at that first fraction, what do you notice? Greatest common factor? F of x plus h. So I'm going to factor that out. Yes, Chanel?
This is just a general question about the test, but do we have to do proofs on the test?
Nope.
Okay.
But why am I wasting my time doing this?
So we understand how it came from the long run?
Yep. But also, most of you are going to end up taking multiple calculus classes in college, right? I'd say it's probably about 50-50 odds that your professor is not going to give one hoot about numeric problems and very likely will assign all of the proof ones. So I do want to make sure we're doing some of this so that it's not completely foreign if that's the calculus course you land in. Now, maybe 50-50 is too high of a proposition, but if you're a tenured full professor at a research university, you don't give one hoot about the numeric problems. All you care about are the proof problems. Because what you've spent your lifetime doing is proving things in mathematics. That's what high-level mathematics is all about. They don't give a rip about problems. They care about learning new things, proving something that you didn't know was true. It's very high likelihood you'll land in a course, especially if you have to do through like Calc 3 if you're an engineering student, where you're doing a lot of proof at some point. So I want to do some of this now so you get used to what it looks like and what it feels like, okay? Just as an aside, explaining why I'm not, you're like, Mr. Kulik, I take your word for it. Like, I believe you that this works. Don't even have to prove it to me. I'm doing it for a reason. Okay. If I look at the next fraction, I notice the same kind of thing, right? Okay. And now I'm going to use some limit laws. So I know that the limit can distribute to the product and it can distribute to the sum, right? So I'm going to write this now as 4 limits. Oops. that's supposed to be an H. Okay. Now let's do some derivatives, or some limits, excuse me. What's the limit as h approaches 0 of f of x, or f of x plus h?
F of X.
That's just f of x. What's the limit as h approaches 0 of g of x plus h minus g of x all over h? What? Nope. Every single one of you knows what this limit is.
Oh, that's just the basic equation, isn't it?
Basic equation,
Of a derivative,
yeah.
Yeah.
So what is that?
f of prime.
G prime, you
Oh,
mean?
Yeah, because it's g.
Yeah, that's just g prime of x. Oh.
Oh.
What's the next limit?
G of
G
x.
of X.
And what's the last limit?
F prime of x.
And what do we have? That's the product rule from above. There you go. So far, so good?
Yeah.
Let's practice using this now for actual problems. Because that's what the AP is going to ask you to do with it. That's the majority of the questions I'll ask you to do with this. Let's do some of these. All right, so f of x is x times e to the x. Notice that there's nothing algebraic I can do to try to turn this into a power property, right? I can't somehow get those x's into one place because one is a polynomial, the other is an exponential. Those don't mix. Everybody's okay? So what I do is I'm going to think about this as like a g of x and an h of x. What's the derivative of g of x?
X.
1. And the derivative of h of x? E to the
Wait,
x.
wasn't that a rule?
That was one of the derivative rules from last time. So this is g of x times f prime of x. I'm sorry, that's not the way we wrote it in the formula. Let's keep it the same so nobody's confused. F times g prime plus g times f prime. So f was, I guess I used h's and g's here, folks. Or g's and h's. Let's say g, h, h, g. There. HGTV. So I have x times e to the x plus e to the x times 1. So x e to the x plus e to the x. Everybody's okay? That's it, I'm done. Yeah, derivative's done. Derivative's done. Notice here that this is really just the derivative of f was just f of x plus e to the x, right? What do you think the second derivative is going to be?
The derivative of f of x plus e to the x.
Great.
So
And what's the derivative of f of x?
E x dx.
Well, let's write it that way, just f of x plus e to the x, right?
why are there two e to the x's?
Well, when we differentiated this one, that's that one.
Okay.
When we differentiate that, we get that. But that is this.
Oh, in this case, like
The second derivative. I'm doing the second derivative, right?
Okay.
So I did it again. Because what were we asking in B?
The n.
The nth derivative.
Yeah.
So how am I going to figure that out? Well, I'm going to do you know, like the first, second, maybe the third derivative if I need to, try to get a handle on the pattern. Who sees the pattern? Let's look.
You just keep adding in e and x.
Yeah, that's right. So the first derivative was f of x plus e to the x. Second derivative was f of x plus 2e to the x. The nth derivative should be f of x plus n e to the x. Yeah, that's it.
Mr. Bullock, I still don't understand why you added that second e to the x in the second derivative. Sorry.
So were you good with this?
No. It was because, was it because,
So if I differentiate this, I get f prime. When I differentiate this, I get e to the x.
okay,
Right? So that should be the second derivative, is the first derivative plus e to the x.
okay,
Good? Does that make sense?
yeah,
What's the first derivative again?
that. That was,
F of x plus e to the x. So I have this e to the x, and that is f prime of x.
okay, wait, I'm still not understanding that. Where did you get the first e to the x from? The one where it says f prime x plus e to the x, where'd you get that e to the x from?
So the second derivative is the derivative of the first derivative, right?
Okay,
So this is the first derivative right here.
okay,
If I differentiate this, I get f prime.
okay.
When I differentiate this,
Oh, okay.
I get e to the x.
Okay, okay,
Is that?
got it.
Okay. Let's do the next example. Differentiate the function f of t equals root t plus or times a plus bt. Does this look like a product rule to you?
Kind of.
Yeah. Does it have to be a product rule though? No, right? What could we do instead? I could distribute this through, right? And then, well, here, that's just now a power property, right? And t times root t, well, those can combine together, right? What's t times root t?
3/2.
T to the 3 over 2. And now I can just do the derivative using the power property. Now let's write it this way. Oops, I meant B there. Or if I wanted to, a over 2 root t plus 3b over, 2, and that should be root t up there. Notice that, but could I have done this as a product property?
Yes.
Yeah, right? Just like I could swap this fly with a handgun, but it's a little bit more powerful of a tool than I need for that particular task, right? Fly swatter will be just fine, or like a rolled up newspaper. I don't need to pull out a handgun to take care of this fly. I could, it'll work, but it's like more ammunition than I need. You see the analogy? Now, could I still do this with the product rule? Yeah. Is it going to be much worse? Probably not. Okay. Let's look at example 3 here. This is a very common format on the AP exam, is to give you a question like this. F of x equals square root x times g of x, and then tells you g of 4 is 2, g prime of 4 is 3, and we want f prime of 4. So to do f prime of x, I have to do the product property here, right? Because square root x and g of x are distinct functions that cannot be combined. So I'm going to start by rewriting square root x as just x to 1/2. So f prime of x is going to be g of x times the derivative of 1/2, or x to the 1/2. And then I have x to 1/2 times the derivative of g of x. If I want to do f prime of 4, I can do that. And what's g prime of 4? Or I'm sorry, g of 4.
2.
2. All right, here's the $1 million question. 1/2 times 4 to the negative 1/2 is
4.
1/4. Right? 4 to the negative 1/2 is 1 over the square root of 4. So 1/2, and then 1/2 times 1/2 is 1/4. 4 to the 1/2 is?
2.
G prime of 4 is? So when I multiply those together, I get 6.5. Super common format for an AP exam question. Screams multiple choice, no calculator. That's what that screams to me. Because there's no way to get around not using the product rule. Next shortcut. Suppose we have the quotient of two functions that cannot be simplified into getting x in one place. So for example, say we have x over e to the x. Can't combine those into x in one place. We'd use the quotient rule. So the quotient rule is just saying that, like, the derivative of f divided by g is g times f prime minus f times g prime over g squared. Let's do an example. Much like the product rule, I would start by doing everything kind of separately and then putting it together at the end. So here my f of x is going to be the numerator and my g of x will be the denominator. What's the derivative of f?
2x plus 1.
And the derivative of g?
2x squared.
And by 2 you mean 3.
3x.
And you guys all know how to do this, right? Nolan's just the only one answering right now. It's okay. It's the end of the day. I get it. So y prime is going to be g times f prime minus f times g prime over g of x squared. If this is a free response question for me, you could be done here. Is this what the answer on the multiple choice is going to look like? No way, Jose. What are they going to do?
You're gonna make you boil it out?
The numerator, at least, because so that we can combine any like terms. So if I FOILed out the numerator, what am I going to get? I'll have 2x to the 4th
Plus x cubed.
plus x cubed
Plus 12x plus 6.
plus 12x plus 6 minus
3x to the 4th. 3x cubed minus 6x squared.
And then if we push that negative sign through, we do that, right? So my multiple choice solution should be, let's see, I have 2x to the fourth, negative 3x to the fourth, so that'd be negative x to the fourth. I have 1x cubed minus 3x cubed minus 2x cubed. Then I have plus 6x squared plus 12x plus 6 all over this mumbo jumbo. And I wouldn't FOIL that out. Is that okay? This is the recommended way to do it, is to do them separately, each piece separately, and then put it back together at the end. Let's do another one. Here we want to find the equation of the tangent line to the curve, y equals yada yada yada, at the point 1 comma 1/2 e. So if I want the equation for the tangent line, what do I need?
The derivative?
Well, I need the slope. To get that, I need y prime. So let's call f of x the numerator and g of x the denominator. So f prime is e to the x. G prime is 2x. So y prime is g times f prime minus f times g prime over g squared. And I'm not going to bother simplifying this. Why would I not bother with it?
It's really complicated.
Well, it's not my final answer, right? I'm just using this to get the slope. So, like, who cares? What am I going to plug in for x to get the slope? 1. So what do I get here? So slope 0. So what's the equation of my tangent line then?
Yeah.
That's it, right? Bloop. Could you write it in slope-intercept form or point-slope form or whatever? Sure. But if the slope is 0, it's just the horizontal line. So it's just y equals a constant. What constant will it be? Whatever the y coordinate is that, for any point on that line. Well, I have one point on the line. What's that one? Everybody's okay? The last thing I have here is just a summary of the derivative rules we've seen to this point. So this is just all your derivative rules just in one place that we've seen up into this point. That's kind of nice, just having them all in one place as a reference point. Should you have these ones memorized?
Yes.
Yes. Am I going to ask you to write them down? No. Should be able to use them? And in combination? Yes. Right? Like every time we've done the product or quotient rule, we've used one or more of these simpler derivative rules in combination with it, right? Like to do the derivative of the top or the derivative of the bottom, or to do the derivative of one factor or the other factor. We've used these other derivative shortcuts. So we got like 10 minutes left. I want to talk a little bit about this test coming up like Thursday next week, right? I think is this tentative scheduled day I have for that. So I have in the content library, I have the same gist of stuff that we had last time. So I have like 2 parts, a no calculator part, calculator part. So same kind of format. You have some multiple choice questions and a free response with no calculator, and then some just regular problems and another like free response style question that's like multiple parts. Skills you should be able to do. Homework questions you'd want to make sure you look over. But This time I've also included some stuff, additional stuff on the MyAP. So I have a whole mess of multiple choice questions that I thought were good ones that I picked out personally to practice on. Now I made them in the MyAP site, but I also put them in the content library also if you're more interested in doing stuff by hand, if that's easier for you. They're in both places. Just trying to make the studying easier for you. I would do them in the MyAP site because it'll grade it for you. You don't have to grade them by hand. I have the answer key at the bottom. But I had to write that by hand, so I apologize if I got any of the numbering wrong. I'm sure somebody will find out quickly and let me know. And then I have some free response questions that I pulled from the AP site and I put here in the content library. I didn't make this an assignment on the MyAP because didn't have anything that was auto grading that I felt like was what I wanted. So I pulled these questions specifically and just put them in here for you. I don't have the key written up for that yet. One thing that I would say here, though, is if I look at all these skills, one thing you're not going to see, or one thing I want to point out, is right here. I will not require you to use the limit definition of a derivative to find a derivative. Cool! However, you may need to use that definition to demonstrate differentiability of a function, or you might use it to evaluate a limit. So like on the AP exam, I don't recall places where I see people using the definition of the limit directly to do something, other than like writing down the form of it. But I do see stuff like this. So let's say we have plus. You know what this looks a lot like to me when I see this? That looks a lot like this. Where, okay, maybe f of x is this. And I want to check, is f of a 77? It is, right? So this would just be the derivative of f evaluated at 7. So that the derivative of x squared plus 4 evaluated at 7, which would be 14 plus 4 or 18.
I didn't understand the question.
So what I did was, rather than trying to evaluate this limit directly, if I tried to do direct substitution, you're going to get indeterminate 0 over 0.
Yeah.
I recognize that, hey, that's in the form of a definition of a derivative,
Okay.
right? It looks like this.
Okay.
To check if f of x is x squared plus 4, is 77 just a plugged into f? So I checked that down here, and it was.
Okay.
So the answer to this limit is just the derivative of x squared plus 4 with 7 plugged in.
Because that's the derivative definition? Is that why? Okay.
So that's how I did the limit, was I just did the derivative of x squared plus 4 and then plugged in 7.
Okay.
And that's massively easier than trying to do that other thing by hand.
Yeah, you're gonna have to do, I don't even think you can factor it. So-
It would not be pleasant. You'd have to do like a completing the square thing, I think, to do it. And it would not be a lot of fun. Alternatively, we could use L'Hopital's rule, but you don't know what that is yet.
No, we'll be voted about that.
Mm-hmm. It's a good one. You'll be happy to know it.
Okay, is it an easier rule? Or-
It's pretty useful.
Okay.
It's pretty useful. And this, I would say, is something that's like fair game. I'm not asking you to use the limit definition to do this, to do the derivative. In fact, we're doing the opposite, right? We're using the shortcut to get around using the definition of the limit, right? We're going the opposite way. But that is something I would consider like, would I put something like that on the test? Absolutely, yeah. Because that one's teaching us to work smarter, not harder, right? Like I'm using the definition of a derivative in a way to avoid having to do a limit. Yes, sir, I like that. So anyways, yeah, so that's that. So 3-2 is, there's the homework set for this. We'll do the homework quiz next time. Take questions from you guys. We can talk more about test format if you want, but I would just give you the rest of that time to grind away at probably some of these MyEP questions. How many questions is that? This right here, I didn't count them. It's kind of a lot because I have that 3 through 25 odd. But like part of it is just like we need to practice using the product rule and the quotient rule and stuff. Like you just need to do that a little bit. And those are just like do the derivative, do the derivative, do the derivative, just use the shortcut, use the shortcut, use the shortcut. So they're not terribly long. Chanel?
Is this Sunday as well?
Yeah.
Okay.
Yeah, so Sunday there'll be 3 sets due. 2-8, 3-1, and 3-2. But then there'll be nothing next week.
Yeah, that's true.
Because it's just a test.
Nice.
So if you have some catching up to do, I mean, you have the test, but just studying for that, that'll be enough work. Correct.
Okay.
So that's still an option, yes.
I'm just curious, are we starting a new unit, like the one day that we're there next week? You know how we're there for like that A day, B day, and then there's 3 days off? Like, are we starting a new unit on that day?
Probably.
Okay.
Yeah, because it's just like continuing in chapter 3.
Oh, okay.
Right, you know, like we're just going to be starting 2-3, which or 3-3, which is more shortcuts. So it's just like, here's some more shortcuts.
Okay.
And we can't do much with these shortcuts until we do 3-4, because that's where all the fun stuff starts happening.
Oh man.
Where we can start nesting like one function inside of another.
Wow. Okay.
And maybe you have like one inside of another. Like you have like a bunch of functions nested inside of each other, one inside of the next one. Like the square root of cosine of x squared. Which will be like just a ton of fun. That's the best stuff. But that's as hard as the derivatives get.
Okay. But you said this one's getting hard at which one of these are like the hardest?
Dear Heavenly Father,
Oh,
as the school day comes to a close, we gather before you in gratitude for the time we've spent learning, growing, and building connections within this community. We thank you for the knowledge gained, the challenges faced, and the moments of joy and discovery. Lord, we ask for your continued presence and guidance as we leave this place of learning. Be with each student as they return to their families and homes. Keep them safe from harm and grant them a peaceful evening filled with rest and rejuvenation. We also pray for our teachers and staff who have worked tirelessly to educate and support us. Bless them with the strength to continue their noble mission and inspire them with creativity and patience. We entrust our lives and this school into your loving hands, Lord. Watch over us until we gather here again. In Jesus' name we pray. Amen.
Have a blessed day, Notre Dame, bro.
Chanel, the hardest thing in chapter 3 is 3-9. which is on the fourth test.
Oh, okay.
If you look, it's not down here till.
Oh, okay,
Down
yeah, I
there.
can kind of see why it's hard, so. It's long.
Well, it's mostly because the hard part is writing the equations.
Oh, really?
Because these are like all story problems.
Oh my god, I think that looks really scary. Ready for that? Bye.
But it's not that bad because they're all kind of the same.
That's good. It's a subjective statement. I think that's around November, right? November 4th class?
Probably would not be. I mean, we've been going about like a month a chapter or a month a test is kind of how this is played out, right? We did most of August or most of September most of August to do one, most of September to do the next one. Probably be most of October to do the next one.
Yeah. Hopefully we're not on time. I was for 3.9. So.
Well, I record them all for you.